I will begin with a word of prayer. So let me start. Heavenly Father, we thank you for this day. I thank you for these students, Lord, and just ask you to bless us class today, Lord. In your name I pray. Amen. Yeah. Ooh.
He's like a 1 point in task.
Ooh.
Just despite him. Let's get 5. Oh, okay, 5.
A little bit into class. Let's see here. So let's talk about the binomial series. This is I could recount the things we already know, and I probably should, but we'll do that maybe afterwards. I'll say it in words. We already know power series for sine, cosine, cosine, exponential, and then we can derive all sorts of series using geometric series techniques, right? We know how to find the reciprocal series using long division. We can multiply series is also an important technique. I mean, we've got all kinds of options. Of course, there's also Taylor's theorem, right? So Taylor's theorem is important. Binomial series, I'll start by talking about the more basic version of this, which is the binomial theorem. What's the binomial theorem? If we have a plus b to the power n, what is it equal to? So let me show you. We do 1, 1, 1, 1, 1, 1, 1. There's a 2 here. 3, 3, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6. Can you tell me the next row? 15, 20, 15, 6, 1, right? So a plus b to the n is equal to the sum, k equals 0 to n, of n choose k, all right, a to the power n minus k, b to the power k. So this quote-unquote n choose k is something you'll also study in another course, right? Your probability and statistics course, right? Some of you guys done that? Is this at all familiar? Let's see here. Specifically, this would be like 6 choose 0. This is 6 choose 1. This is 6 choose 2. This is 6 choose 3. This is 6 choose 4. This is 6 choose 5. And this is 6 choose 6. So you can figure out these are the so-called binomial coefficients. All right. So I mean I can tell you some things sort of generically without like a lot of work. What this looks like, of course, is a to the n plus n a to the n minus 1 b plus plus n a b to the n minus 1 plus b to the n. You know, so this is stuff that happens in the middle. It's a little bit complicated, but you can easily figure it out for a specific choice of n, right? For example, if I chose 1 plus x to the 4th, what would it be equal to? So I can use this one right here to quick multiply that. This is, what is this called? Whose triangle is this? Pascal's triangle, yeah. So, but I think it belongs to all of us. 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth, okay. Do you guys know what the formula is for n choose k? There's a formula you can write down for the binomial coefficients in terms of a ratio of factorials. Does anyone know that from their probability and stats class, the formula here? That's no fun, because I don't remember it. All right, now we'll play the guessing game. I'm guessing k factorial over n factorial times n minus k factorial. That's my opening guess. Does it work? Choose something somewhat difficult, like 6 choose 2. There's a question mark here. I'm not sure. I just made that up, guys. Doesn't look good. Definitely looks like I should have n factorial upstairs. Definitely need n factorial upstairs. These should be like bigger than 1, not smaller. All right. What we got? Okay, that can't be a coincidence. There you go, formula. I mean, general bit of studying advice, if you forget a formula, but you have some sort of fuzzy memory of it, what do? Check it against something numerical. Yeah? You're like, I would Google it. I know, but remember, this is not an online class, so you can't Google during the test. Right? Okay. Anyway, there it is. That is the, for what it's worth, the formula for the binomial theorem. Okay, so this is just, classic algebra. And the thing that distinguished Newton, say, from Pascal and those that came before him, is he figured out that, you know what, you could still make sense of this if you had like 1 plus x to the alpha power, where alpha is, a real number. Maybe alpha is not an element of the natural numbers. Maybe it is, maybe it isn't. Now, if alpha is a natural number, right? If alpha is a natural number, then we know how to expand this already, right? The binomial theorem says if you have 1 plus something to an integer power, you can just look at Pascal's triangle and expand it. You get finitely many terms, right? But binomial series says, well, it's a series. So let's call this thing f of x, all right? We'll say 1 plus x to the alpha power. We want to calculate the Taylor series for f of x centered at x of 0 equals to 0, okay? And you guys remember what that was? Remember, TF of x was the sum k equals 0 to infinity of the kth derivative evaluated at 0 over k factorial times x to the power k. I'm going to write it as a sum over k so that we can see the connection with the binomial theorem most manifestly, all right? Okay, so what's the first derivative? F prime of x is what? Right? We can differentiate power functions. Agree? So alpha times x, 1 plus x to the alpha minus 1, times the derivative of the inside function. What's the derivative of the inside function here? What's the derivative of 1 plus x with respect to x? It's just 1, right? So that's not especially exciting. F prime prime. Alpha times alpha minus 1, 1 plus x to the alpha minus 2, right? And I shouldn't have written this here. By now I should have learned that I should leave myself a column right next to my list of derivatives so I can evaluate next door and keep my work nice and organized. So this is poor planning on my part. My apologies about that. It was for a good cause, but you know. So I'll start evaluating. What's f of 0? One to the alpha, right? Also known as 1. What's f prime of 0? Looks like we got an alpha. What's f prime prime of 0? Alpha times alpha minus 1. Right? All right, differentiate again. F prime 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 of x. We've got alpha times alpha minus 1 times alpha minus 2, 1 plus x to the alpha minus 3, right? So what's f prime prime? Prime of 0. Or let me write that the third derivative at 0 is alpha times alpha minus 1 times alpha minus 2. I think by now the pattern is pretty much evident, right? If we take k derivatives, what are we going to get? What's the kth derivative at x? It is alpha times alpha minus 1 times alpha minus what? Alpha minus k plus 1, right? Or alternatively, you could say alpha minus parentheses k minus 1, if you prefer that. All right? 1 plus x to the alpha minus k, right? So what is that? What does that give us over here? The kth derivative evaluated at 0 is alpha times alpha minus 1 times alpha minus 2, alpha minus k plus 1. And that is all we need, right, to write down the Taylor series. What's the Taylor series for 1 plus x to the alpha? So assuming, of course, that f of x is equal to Tf of x, that is f analytic at x not equal to 0, right? We have the following. We have that 1 plus x to the alpha is equal to the sum k equals 0 to infinity of alpha times alpha minus 1 times alpha minus 2 alpha minus k plus 1, all divided by n factorial x to the power k. That is the binomial series. Not that hard to derive from Taylor's theorem, right? Not that hard. That's why a lot of books have this as a homework exercise. But I think that falls short. Like, this should be a section in the book. It's an important series that has many applications that you'll see as you use calculus theoretically in engineering courses. This is one of those things that you actually use a lot, especially in physics and so forth, wherever approximations are made. The first three terms in this are 1 plus alpha x plus 1/2 alpha times alpha minus 1 x squared. And then what's next? This is the first four terms. 1/3 factorial alpha times alpha minus 1 times alpha minus 2 x cubed plus dot, 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 dot. So any questions? So I told you last time that the power series, I told you that the function sine, cosine, cosh, sinh, exponential, these are all quote-unquote entire functions. That means that their power series represents the function for the entirety of the real numbers. This, in contrast, is not an entire function, not usually anyway. Yeah.
The n factorial in the denominator,
Where did the n come from is a very good question. The answer is the fall of man. So, yeah, that's definitely supposed to be a k factorial. Sorry about that. So sorry. Yeah. So, I mean, comment. If alpha equals to n, right? If alpha equals to n, and n is a natural number, notice alpha minus 1, alpha minus 2, dot, 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 alpha minus n, good grief, alpha minus k minus plus 1 divided by k factorial. Let me give that a name because I don't want to write it again. I'm going to call that whole thing right here Pac-Man. So Pac-Man is equal to this, right? But what could you do to that? How about you just multiply the top and the bottom by, let's see here. What if you keep going in the top? You go add to that alpha minus k, alpha minus k minus 1, dot, 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 3 times 2 times 1. And if we do that upstairs, we have to do it downstairs too, right? So if you do that, what does that put upstairs? That would be alpha factorial upstairs. And downstairs, we would have k factorial and alpha minus k factorial, which, of course, you could recognize if I rewrite it as n factorial times k factorial times n minus k factorial. So as you can see, this formula agrees with the binomial coefficients in the context that it should, namely that the power we're expanding by is a positive integer. Taken a different way, we've just proved the binomial theorem using calculus. I mean, this is a calculus derivation of the n choose k formula. Admittedly, I have not explained its like combinatorial interpretation, right, in terms of choosing k things from n things, with or without repeats. Which was it? Yeah, okay. That's not this course, thankfully. I'm really bad at that stuff. Okay, so anyway, there you go. Now, some calculus books will be very sort of cute and write, instead of writing what I wrote as, the Pac-Man, they'll replace this with something like alpha choose k. They'll just say this formula defines, quote unquote, the alpha choose k symbol. I try not to do that because I want to reserve the n choose k symbol for when both of the inputs are natural numbers. In contrast, this makes sense even when alpha is like 3.5 or whatever. Yep. I multiplied the top and the bottom by the same thing.
How did you get that Pac-Man from Pac-Man?
That's what we have here. In the purple, think of this as being all purple. The purple part is up here. Okay, so application, what if we wanted to find the power series expansion for, say, 1 over the square root of, 1 minus x squared? Let me start us out simpler. No. I'll start out simpler. 1 plus x. There we go. Now it's actually the same. Let me just make it the easiest kind of example. So that's 1 plus x to the power what? Negative 1/2, right? So the first 3 terms in this are what? 1 plus 1/2. Oh, wait a minute. I can't do math. What is alpha? Alpha's minus 1/2, right? So I go 1 minus 1/2 x. What comes up next? Plus 1/2. I'll do some parentheses. Minus 1/2. And then what's minus 1/2 minus 1? Minus 1/2 minus 1 is minus 3/2, right? X squared. Oh, there. I'll do the first 4 terms to make sure we understand what we're doing. 1 over 3 factorial, which is 6, minus 1/2, minus 3/2, minus 5/2, x cubed. This is the pattern. So there's the first 4 terms. Of course, I can clean it up, right? That gives me 1 minus 1/2 x. What is that? Plus 3/8 x squared. What do I got here? Minus 15/16 x cubed plus da 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 da. There you go. So why is this example, why is this discussion important? Can you do this example with geometric series? No, geometric series doesn't treat reciprocal square roots, right? It's outside the scope of our geometric tricks. Think about it. Is it a sine? Is it a cosine? Is it anything related? It's none of that, right? So this is another kind of example that really is best dealt with the binomial series. So this is the cool thing, right? When the power that you're raising to is not an integer, it doesn't truncate like with Pascal's triangle. We only need as many terms as the power, right? Well, plus 1, I guess, n plus 1 terms in the power n. In contrast, if you have a non-integer power, it goes on and on and on forever, right? So as part of the creative genius of Newton was understanding this and using it to prove other things. But yeah.
Like, how did you get that series?
It's this. I plugged in alpha equals to minus 1/2 into here. I'm just using what we just did. Now, the so here is the not so nice looking general thing. 1 over the square root of x, 1 plus x. is the sum k equals 0 to infinity of, well, minus 1/2, minus 3/2, minus 5/2, dot, 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 minus 3/2, excuse me, minus 1/2, minus k, plus 1, all divided by k factorial times x to the power k. That's the full Maclaurin series for this function. It ain't pretty, but there it is. I mean, I could make it a little bit prettier. We could pull out, you could simplify this a bit, right? Can we make this formula nicer? What would you do to the last term to make that prettier? How can we rewrite minus 1/2 minus k plus 1 as minus something divided by 2? Fill in the blank for me. What should we put there? I'll get you started. 2k. And that gives me a plus 2. There's a minus 1 here. 2 minus 1 plus 1. How many terms do I have here with a minus? How many negative terms do I have there? Count them. How many? 5. No. You got to think about, in terms of k, how many negative terms here? I think there's k, right? The k equals 0 term is plus, k equals 1 minus, k equals 2 plus, k equals 3 minus. I believe the sign is minus 1 to the k. So we could write this more elegantly, nicely. It's minus 1 to the power k times the product of odd integers, right? 3 times 5 times 7, dot, 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 times 2k plus 1, all divided by k factorial times what? How many 2's do I have? Yeah, don't be distracted by this formula up here at the moment. That's a simplification of what I'm doing at the moment. I'm just counting the 2's from these purple factors. 2, 2, 2, 2. There are k of them, right? So 2 to the power k. X to the k. Could you play further games with this? Could you simplify this further? I mean, you could, but I think this is a perfectly legitimate, this is a pretty clean formula for it. You could play the game that you cancel all the odd factors in the, you could play more games with it, but this is a pretty good formula, I think, if I haven't made some silly mistake. So, yeah.
Can you write the product of the odd integers as a factorial?
I don't, if the thing is, I don't think I can, how can I, she's asking, can I write the product of odd integers as a factorial? Why not? I mean, not directly. You need the evens to construct the factorial, right? Yeah.
How did you get the first term you want in the top?
Which is ultimately from this. which is ultimately from this. So for those of you who are, wow, Zach is really, see, I thought this was some kind of ploy, you know? Like he's going to show up like 5 minutes later or something, but no, this is really an opportunity. It's really not coming. All right. Okay, so listen, at the moment, you could, of course, just calculate this directly with Taylor's series. It wouldn't be much different, right? But let's make it worse. All right, let's make it worse. Let's make an example where if you tried to directly do Taylor's series, it would just be phenomenally horrible. It's not hard to come up with such examples. One thing I could do, I'll even do it over here, simple thing I could do, I can just take my previous example and multiply by x squared. What's the power series for this, centered at 0? See, if you just willy-nilly apply Taylor's theorem, all of a sudden you're differentiating products upon products upon products upon products, right? Now, if you're a slightly more sophisticated Taylor's theorem user, you'll separate off the x squared and then do it. And then it's not too bad. But if you don't, anyway, my larger point is, to get this, just multiply that by x squared. All right, so if we have a known series and we just multiply it by x squared, we can do like that. Third example, still relatively simple. What if I had like 1 plus x squared times 1 over the square root of 1 minus x, or 1 plus x rather. What did I figure out the first 3 terms were? 1 minus 1/2 x plus 3/8 x squared. Was that right? It was minus 15/16 x cubed. So if I wanted to find several non-trivial terms, how would I do it here? First of all, my advice would be ignore the 1 plus x squared to start with. Find the power series for the complicated thing, and multiply. How do you multiply series? Well, how do you multiply a polynomial times a series? Just distribute. So we got like 1 minus 1/2 x plus 3/8 x squared minus 15/16 x cubed. That's all from the 1. And then x squared minus 1/3 x cubed. And that's probably enough. Do I need to write anything down past that? I don't think I do. Why? When I'm distributing x squared, why would I only bother to take x squared? You know, I did 1 times all of that to give me that, right? Up to order 3. I did x squared only times this one and that one. Why didn't I bother with the 3/8 x to the 4th that I get in the multiplication here? Why not include it in what I wrote down? You're like, well, you haven't said what you're doing, so it's hard to know. Fair enough. We are calculating the power series to order 3. So I don't care what happens at order 4. I ignore it. So up to order 3, I have everything I need. That's it. That's all she wrote to order 3. And so you just collect terms. All right, so that's 1 minus 1/2 x plus 11/8 x squared. No. minus 53/48, I think, x cubed. Am I wrong? So what I tried to do was 3 times 15 is minus 45. And then, oh, I was supposed to multiply that by, what's 48 goes into, oh, wait a minute, no, that's not right. Yeah. Oh, man, really? This one's wrong? Oh, you guys are killing me. What is this? 48? Ah, sadness. Oh, man. I mean, it's not that bad, but I wish you guys had told me that when you noticed it, which was like 5 minutes ago, you monsters. You're horrible people. Horrible people. I'm not bringing you. I decided I was going to bring ice cream, but now I'm not so sure. I don't know. 48 is here. Yeah.
For your second set of terms, it says x squared minus 1/3 x squared x cubed. Is it supposed to be minus 1/2? Like we've distributed the x squared? Not on this side, but this side. Like, you have written.
Oh, yes, thank you.
Yeah, the same thing over there. It's just making your multiplication a bit worse.
Whoop. Whoop, whoop.
Second set of parentheses, second row, it's supposed to be.
Oh, right. How did I get a third there? I'm just randomly changing 2s to 3s today. Great. Wonderful. Well, I hope the technique was clear if the arithmetic was not. I'm worried about adding a moron. All right, me, not you. 1 minus 1/2 x. Thank you. Is that, are we good? Okay. What's 1 plus, still 11/8 though, right? All right, so minus 39/48, yeah? All right. Great. So we fixed it. Next example. Suppose you wanted to find the first 3 non-trivial terms in something like, I don't know, 3 minus x to the 4th to the 1/3 power. See, this one, I can't do binomial series right off, right? I need to change it so that it's in the form 1 plus something, right? So once I have 1 plus u to the alpha, that's, well, let's do the 1/3 to be more specific here. 1 plus u to the 1/3 power, that's 1 plus 1/3 u minus 2/3 u times u squared minus 5. Oh, I'm sorry, I didn't do that right either. Grief. Minus 1/3 times minus 2/3 u squared plus dot, 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 dot. Okay, so this I have to factor a 3 out. Factor a 3 out, like that. And if I do that, that gives me the cube root of 3 out front. And then I've got 1 plus u to the 1/3 power, where u is equal to minus 1/3 x to the 4th power. guys got it? You guys see what I did? Then why did I do that? Because now I can use the binomial series result in U. So this is the cube root of 3 times 1 minus, well, plus 1/3 U plus 2/9 U squared plus dot, 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 right? But put what in that is, we're looking at the cube root of 3, 1 minus 1/9 x to the 4th plus 2 over 81 x to the 8th. Get out a sheet of paper. Write your name on there. Bonus quiz. Two questions. Question number 1. What is the third derivative evaluated at 0 for my example 3? Do not differentiate 3 times. I want you to figure it out without the differentiation. Hint, it has something to do with this number, minus 39 over 48. And the fact that that's also equal to the third derivative of 0 divided by 3 factorial. Let me put that into a sentence. Set the f3 of 0 over 6 equal to minus 39 over 48. Solve for f3 of 0. Here, this bonus quiz is only good if people get points. Let's see here, f3 of 0 over 6 is equal to minus 39 over 48. Thanks, Zach, for this hint. There you go. In the meantime, let me get the computer up and running here. I'll allow group work for problem 2. What's the answer? And why? What's the 7th derivative of the example 4 function? What did we just find? We found the Maclaurin series. To order 8 already. Is there a non-trivial 7th order term? There's not. It jumps from the constant to the 4th power to the 8th power. The coefficient of x to the 7th in the power series expansion, for example, 4, is what? It is 0. That means that the 7th derivative evaluated at 0 divided by 7 factorial is equal to 0. So what's the answer? 0, yes. This is the second lecture I have ended with this trick about calculating higher derivatives by looking at the coefficient of a power series. Is this something you need to learn? It is something you need to learn. It's pretty much another way of trying to develop your understanding, your comprehension of Taylor's theorem. It's a kind of sideways way of asking you to understand what Taylor's theorem is saying. All right? Come on, Top Hat. So guys, just to let you know where we're going, I wanted to project my notes. I have some applications of binomial theorem and power series to physics I'd like to share with you, like special relativity and also just regular Newtonian gravity. Like, what's the error and saying f equals to mg, when we know that f is actually gmm over r squared. I'd like to talk about that in light of all the mathematics we've developed. I'll probably do that Monday. And that's pretty much it, besides just talking about your, the amount of time it takes Top Hat to load, it really starts to wear on me. All right, it's finally loaded. There you go, 3579. Because remember we talked about last time, two polynomials are only equal if they match, each coefficient matches, right? Same is true for power series. If the meaning of the coefficient of x cubed is given to be the third x cubed here, puts in the third derivative at 0 divided by 3 factorial. That has to match whatever number goes here. So all I'm suggesting we do is set the third derivative at 0 over 3 factorial 6, equal to the number. And that tells me it's a sideways application of Taylor's theorem is what it is. Anyway, have a good weekend, you guys. Oh, yeah, please pass them up. By the way, I should mention, there's like one other sort of little proofy thing I have left to do with you guys. It turns out that there's some proofs in the handout PDF that are really pretty easy that I should go through with you. They're not that bad.
It really hurts, but
Thank you.
it's just because I'm so weak. I just have to read back into it.
Thank you.
Because it's so sore, just because it's been so
Well, the bonus quiz is more fun if I tell the answers.